Let's look at a simple linear regression example. We've been doing a lot of work in bits and pieces, and let's try to tie it all together here. A study investigated a possible relationship between eggshell thickness and environmental contaminants in brown pelican eggs. And as part of the study, they investigated the shell thickness versus DDT level in a sample of 65 brown pelican eggs on Anacapa Island in California. And this was back in the 70s. DDT was a very commonly used pesticide that was used for a long time, but it had some harmful effects and was eventually banned. Here I've plotted out the shell thickness of the eggs against the DDT in parts per million in the yolk lipid. And we see here that we actually have pretty heavy DDT concentrations, and we also see that there appears to be a relationship between these two variables. And if we plotted this out, we could possibly conceivably fit a line through there. There certainly looks to be a decreasing trend, so let's see what happens if we use our simple linear regression techniques to fit a line through there. To do so, we would use a computer to get our least squares regression line, and this is the output from the computer package R. Different computer packages typically look pretty similar to this type of thing. So we've got our estimates here of our regression parameters, and if you're not familiar with scientific notation, what this is saying down here is minus 8.732 times 10 to the negative 5, or in other words, we shift the decimal place over 5 units, and we get minus 0.0000872. And so our regression line is y hat is equal to 0.4231 minus 0.0000872 times x. Let's see what that looks like on the scatter plot. Here's our scatter plot with our regression line superimposed. And we see this decreasing trend. We're putting it in there, and we may want to use this, possibly use this line for prediction. So let's say we had a brown pelican egg on this island at this time frame, and we knew, suppose, just for the sake of argument, that the DDT concentration is 2,000. If we wanted the predicted value of y for that, well, we simply go up to the line, and we go over here, and we get the y value for that, and that would be our predicted value of y for an x value of 2,000. But more formally, we can actually do this on the line. So here it is. What is the predicted shell thickness for a DDT level of 2,000 parts per million? Well, I simply take my x value here and I sub it into my line, and I get this for a final. So my predicted shell thickness is 0.24846 millimeters. Here's a different type of question. What proportion of the variability in eggshell thickness can be explained by the linear relationship with DDT? Sounds a little complicated perhaps. How are we going to figure that out? Well, let's look at a plot. Here's our relationship again. There appears to be a decreasing trend. Shell thickness has a high of about here somewhere to a low of about here somewhere. And there is this decreasing trend. Part of the variance in shell thickness is due to that decreasing trend. We could draw a line through these points. Part of that is due to that decreasing trend, but part is just due to random variability of these points about the line. And mathematically, the part due to the decreasing trend that we see there is r squared, the coefficient of determination, which also happens to be the square of the correlation coefficient. And that can be found in computer output. So if we go back to our computer output here, I have something called multiple r squared, which in a simple linear regression is simply r squared. And that is 0.3202. And that is the proportion of the variability in y that can be explained by our linear relationship with our x variable. Or in other words, 32% of the variability in eggshell thickness can be explained by the linear relationship with DDT. Here's another question. Suppose we want to now do some statistical inference. Before doing that statistical inference, we want to check our residual plots to see if it is reasonable to do that statistical inference. And we plot out our residuals, which are the difference between our observed values and our predicted values from the model. And those residuals should show things like constant variance and normality if our statistical inference techniques are to be valid. And here's a plot of the residuals on the y-axis against our DDT, our x, on the x-axis. And what we're looking for here, do we have constant variance? And I'm looking here and I see pretty constant variance, not too much on the go, nothing too wacky. There's not a great change there, so I think that constant variance assumption is probably looking pretty reasonable. Are there any major outliers or anything like that? No, that side of things is looking pretty good. Is there any major curvature or anything like that? No, everything's looking fine as far as I'm concerned. So that residual plot checks out to me. Now what about normality? Here's our normal quantile plot, and if our residuals are approximately normally distributed, this should be approximately a straight line, and it is, to my eye. I think that checks. So I think we can go ahead and do some statistical inference techniques and feel reasonable about it. Suppose we want to test the null hypothesis that there is no linear relationship between y and x. And what that means in simple linear regression here, that's the null hypothesis that the true slope is equal to 0. And we're going to look at our output here, and what do we get? Well, this is our beta 1 hat. And this, right beside it, is the standard error of beta 1 hat. And why is that important? Well, our test statistic of this null hypothesis is simply beta 1 hat minus 0, our hypothesized value, over the standard error of beta 1 hat. And so I could put all of this in. This would be minus 0.00008732 minus 0 over 0.00001603. This number here. Now, if you throw that into your calculator, you will see that this is minus 5.448. And I didn't actually have to do that because that is also given in our output here. That is also given in our output. And the corresponding p-value is right there. That is actually given there. That is testing our null hypothesis that we want to test. And so our p-value here is equal to 9 times 10 to the negative 7. That's what that's saying. Or in other words, 0.00000009. That is a very, very small p-value. And that means that there is very, very strong evidence against that null hypothesis. Very strong evidence that this true slope is not actually equal to 0. What does that mean? Well, our sample slope was negative. And if we look at our plot, there was a decreasing trend. And so we got a tiny p-value of the test that the slope is equal to 0. And so what we are saying is there is very strong evidence that that is a real effect. And there is a real relationship between DDT and shell thickness. And that the shell thickness tends to decrease as DDT increases. But keep in mind that this was an observational study, and so we cannot say that there is a causal link, that the DDT was actually causing that decrease in shell thickness. It may very well be the case, but this type of analysis cannot reach a conclusion that strong.